We are in Rosen, section 13.3 on Turing machines. And these are the topics covered in this section. We will only discuss the definition and an example of Turing machines in this video. There are other videos that address other sections. And of course, you will want to do the readings. Turing machines are named for the great mathematician Alan Turing. There's a biography in your textbook that I recommend you check out. And what is a Turing machine? Informally, Turing machine consists of a control unit that can be in finitely many states. It has an infinite tape in both directions divided into cells, and we see these items depicted at the bottom where the states have some kind of indicator in the control unit, have a read and write head, and then this tape that divided into cells that extends both directions infinitely in distance. And as suggested, the head not only reads what's on the tape, but can write back to the tape, changing the symbols that it reads, and then it can read them again. They're more powerful because of that infinite memory represented on the tape, unlike finite state machines, which have only finite memory. And also because prior output can become input, gives these a greater power than finite state machines. And they really are the most general models of computation. They can do whatever a computer can do, but actually they can do more because of that infinite memory capability. Okay, well, more formally, how do we define a Turing machine? A Turing machine is a four-tuple. It has a set of states, has an alphabet. It's an input and an output alphabet. Always contains the blank symbol B. It has a partial function from the state and input, or state and alphabet, to the state and alphabet cross product, but we add a direction. So in the first two, it's very much like a finite state machine with output, but when we add the direction and the ability to change the input with our output, we really do get a more powerful machine. Identify a starting state. Typically, it's S sub 0. And the partial function is the heart of the Turing machine. It's the function that does this mapping from S cross I to S cross I cross direction. So we read a symbol that we're in a certain state, and if our function is defined, it may be undefined. Then there's a unique state and symbol and direction associated with that pair. And that results in a 5-tuple corresponding to the partial function. So that's 2 inputs to this function, 3 outputs from the function give us the 5-tuple. And these are the transition rules of the machine. You could think of it as how we program the machine, but they really do define the machine. And here's how they work. If we're reading an input and we're in a specific state, then our function will cause us to go into a new state, write that output x prime, and go in the direction D. So when we read x, we go into state S prime, we write symbol x prime in the current cell, and we have to erase whatever's there. Each cell can only contain one symbol. And then we move either right or left along the tape. And so here's how the 5-tuple looks. Input state, input from the tape, resulting state, output to the tape, and direction. And then we define a Turing machine by specifying all the 5 tuples needed to do what we want it to do. If the function encounters a pair for which it's not defined, the Turing machine will halt. So if there's an input associated with a state that doesn't exist in our function, or if there's a state that doesn't exist in our function, then it will halt. How do they start? Well, we always start in the initial state S0 and then over the leftmost non-blank symbol on the tape. There are some machines that start at an arbitrary place on a blank tape. We won't address those until later in the homework. This is the initial position of the machine. Let's take a look at an example. Here I've got a set of 5 tuples that define my Turing machine. My alphabet appears to be 0, 1, and blank. I have 3 total states, but notice that not all of them occur in the first, 4 total states, S0 through S3, but not all of them occur as inputs to my 5-tuple. And we'll look at how this machine runs on tape A, which is the input. And we start at the leftmost non-blank symbol. What is the first execution of the Turing machine? Well, we have S0 and S and 0 as the input, so we will start at where I have highlighted in yellow. And what happens is I stay in state 0. I write a 0 over the 0 that is there. You could say that it leaves it unchanged, but we just write the same symbol on top of a symbol if that's what is called for. And then I move the control head to the right, and that is the result in situation B, where the control head is moved to the right and left the 0 unchanged. All right, well now what does our Turing machine do? I'm still in state 0, but now I'm going to be looking at the second 5-tuple where I'm reading a 1 in state 0, highlighted in yellow. And what happens? I go into state 1, I write a 1 and move right. So I leave my tape unchanged, but I go into state 1. And now what 5-tuple do I execute? I'm in state 1, I read a 0, the highlighted yellow 5-tuple says I'm going to go into state 0, write a 0, and move right. So far I haven't changed any of my output. Well, I've been here before. I'm in state 0, I'm reading a 1. So I go into state 1, I write a 1 and move right. Now this is a new place. I'm in state 1, I read a 1. I'm going to go into state 2, that's the highlighted yellow 5-tuple. I'm going to go into state 2, write a 0 and move left. So now I have changed my tape. Now I'm in state 2 and I'm reading a 1. And I'm going to go into state 3 and write a 0 and move right. And since state 3 doesn't appear as the input state of any 5-tuple, my machine halts. So what did this machine do? Well, the machine read along the tape until it found 2 1s in succession, and then it went backwards and overwrote those 2 1s with 2 0s. And that exhibits some unique features of the Turing machine. I could have constructed a finite state machine that did something like this, but I could not do it where it would actually go backwards and overwrite the input. All right, so that is your introduction to Turing machines.